Okay, again, raise your hand if you need another copy of packet 5. So I will print out a couple more copies tomorrow, and you can pick those up tomorrow. But in the meantime, if you can just follow along and just work out the problems on the separate sheets, and then you can always turn those separate sheets in with your packet 5. You don't have to redo the problems in the packet. So today we're going to work on some 2021 FRQs. I think in class we'll only have time to do probably 2 of them, but your suggested homework is to try to get through all of the 2021 FRQs. That way, the more you do, the less you have to do later. So page 7 through 13 is the range of your 2021 FRQs in packet 5. So I have the FRQ predictions up on the board. I realized that, oh, maybe it's better if I typed it out and then gave you a copy of that. So you guys came in, you guys picked up a copy of the FRQ predictions. Again, the FRQ predictions, I'm not confident that that's going to be the order that you're going to see on your AP exam. What I am confident in is that 85–90% of those topics will show up in your FRQ some way or some form. And if you look at it, the majority of your FRQs are second semester topics. I mean, relative max, relative min, MBT, EBT, those are first semester, but by and large, you're going to have a lot more FRQs that's involving second semester topics. Again, I put those topics, subtopics there as an indication that, those are usually the subtopics that go with those larger stems. But they can appear anywhere. But I think if we have certain expectations as to what could happen, then I think we're just going to be more prepared. And especially something I realized that sometimes you look at a problem and some FRQs just feels like it's out of the blue. It's like, where is this coming from? And that the test writers are restricted to what we learned, right? So maybe that problem is just a strange way to represent this method or washer method. And so, kind of run through the topics that you're expecting them to test on and see if it fits, right? Sometimes the way they present a problem doesn't quite fit what we've seen, but it's got to be one of those topics. Can't pull something that we haven't learned this year, so. Okay, so let's look at page 8 here, number 2. A particle P is moving along the x-axis. The velocity is given by v of t. Now you see this subscript P, that's just to indicate that they're talking about the velocity for particle P. So don't think about, wait, what is that P doing there? It is just to indicate, later on, they're going to tell you another velocity of another particle. And the way they differentiate between the 2 different velocities of 2 different particles is they use the subscript P and subscript Q to tell you which particle they're referring to. Okay. At time t equals 0, particle P is at position x equals 5. A second particle, Q, also moves along the x-axis. The velocity of the particle Q at time t is given by v sub q of t. So here you're given a different velocity function for a different particle. At time t equals 0, particle is at position x equals 10. Now, this is number 2 on the 2021 FRQs. This is a calculator problem. Right, so just to let you know, 1 and 2 are going to be calculators, and 3 through 6 will be non-calculators. Okay, part A. Find the position of the particle P and Q at time t equals 1. Well, if we're given velocity and if we're given the location, we like to use that final equals initial plus displacement formula to help us through with each of our positions. So we're going to use that to help us get through finding particle P and Q's location. So we know final equals initial plus displacement. That's our formula. So if I want to find x of 1 for particle P, I can start with x of 0 because it doesn't mean that we're always starting at x of 0. We're starting at x of 0 because that's what they give us, right? We're only able to provide the initial based off of what's provided, what's given to us. So it could be a 0, it could be a different value. It just depends on whatever they tell us. So in this case, 0 happens to be the given or the initial location. And then displacement is just how much progress this particle has made in that time period. So the integral from 0 to 1 of our velocity function, this goes into your calculator. And we get that the particle ends up at 5.371 at p equals 1. Particle Q, we follow the same similar procedure there. Different starting location and a different velocity formula. Math 9 for each of the integrals there. Part B, are particles P and Q moving towards or away from each other at t equals 1? Explain your reasoning. So there's a couple of things that we want to make sure that we know, right? We want to know, where are these particles located? Are they to the left or to the right of each other? And also we need to figure out which direction they're moving, right? We can't just assume, one's positive and the other's negative. That means they're going to go away from each other. But if they're to the left or to the right of each other, it really depends where they are in terms of whether they're moving towards or away. So we need to figure out, we already know their locations on the x-axis, but we also need to find their direction of motion. So let's find their velocity at 1. And then if we know where they are, and if we know which direction they're moving, we'll be able to visualize it and know whether they're moving towards or away from each other. So positive velocity would mean moving to the right, and negative velocity would mean moving to the left. So we have the velocity of both of the particles. So plug 1 in for both of the particles' velocities and check their signs, place them, know where they are on the number line, and then see if you can convince yourself whether they're moving towards or away from each other. So we know particle P is at 5.371 on the number line. Particle Q is at 8.564 on the number line. Particle P the velocity of particle P is positive. Sine of 1 to the 1.5 is positive, so it's moving to the right. So we know P is moving to the right. And we know that particle Q starts off to the right of particle P. It's all the way over at 8.564, but then the velocity is negative, so it's moving left. So P is at 5.3 moving to the right, Q is at 8.5 moving to the left, and so therefore we can conclude that they're moving towards each other at that moment in time. It's showing you, so I can hang your mouth. Okay, yeah, so you see that that's the x value of 1, right? So I can plug that 1 for that. I use still that's like if I plug forward my x to so we have to figure that out. Okay, I'll try to print one out so I can put it. Okay, any question with B? I think if you can visualize it and know where the particles are beginning and which direction they're moving, I think it's easier to see, okay, it's obviously moving towards each other because of where they're starting and which direction they're moving. Part C says find the acceleration. So we know acceleration is the derivative of velocity. So we can use math 8, use the calculator to get that acceleration value. And then it's asking about increasing, decreasing speed. So then we know we got to compare signs, right? If velocity and acceleration are both the same signs, we know speed is increasing. But if one is positive and the other is negative, then we know speed is decreasing. And then total distance is just the absolute or the integral of the absolute value of your velocity function. So remember these formulas there. Okay, let's look at page 9, number 3. Oh, does anybody still see, you look at the previous one? Part C, sorry, previous problem, part C, the speed is decreasing because my velocity is negative. Meanwhile, my acceleration is positive. So opposite signs indicate decreasing speed. Total distance is just the absolute value, integral of the absolute value of VMT. Okay, page 9. Okay, so, there are going to be some problems that's going to feel more difficult than others, and this is one of them. And if you come across a difficult FRQ, then, don't feel like, oh, I got to get everything right. Otherwise, it's going to be a bad score. You're just trying to do everything you can just to earn as many points as you can. Don't feel like, oh, I got to get everything right. But, just do the best you can. Anything that you can put down, anything that you can identify as a way to earn points, then that's great. I mean, I think to earn in that 4 or 5 range, or to earn something in the 4 range, if you can get 50% of everything, that's basically in that range of a 4. So if you can earn 5 out of 9 points, if you can average 5 out of 9 points for every FRQ, you're in a good spot. So some FRQs you're going to be able to do much better on than others, but definitely try to put as much as you can. But also don't spend too much time on one FRQ. If you're really stuck on something, then go to something else, and then you can come back to it later. Okay, so a company designs a spinning toy using the family of functions y equals cx root 4 minus x squared. I think we get a little thrown off if we see a constant, but just think of that c as like a 2x or a 3x or a 5x. It's just some constant that is hidden from us for now, but we just know that it's potentially, if it's 2 or 3, it ends up maybe stretching the graph a little bit, but the shape is still going to remain the same. C is a positive constant. The figure above shows a region in the first quadrant bounded by the x-axis and the graph of y equals cx root 4 minus x squared for some c. Each spinning toy is in the shape of this solid generated when the region is revolved about the x-axis. So this is only showing a portion, a 2-dimensional version of half of the spinning toy. If we were to rotate this and flip it on the side, it's going to look more like this. It's kind of like a spinning toy with a sharp point at the end, so it can actually spin. So we're only seeing a portion of it. If we were to rotate it and turn it up on its sharp point, then we can imagine the full shape of that spinning toy. Okay, part A, find the area of the region in the first quadrant bounded by the x-axis in the graph for c is equal to 6. Okay, so this is not too bad. We're just finding the area of this quadrant of this shaded region here. So we'll just do top minus bottom. Anytime you see area, you always want to explore top minus bottom first. We can definitely do that since both of these functions, both of these are functions. You have a y equals, and then this is also y equals 0. So we can just simply do top minus bottom here. And again, this is non-calculator. This is number 3 now. Number 3 is non-calculator, so we want to do all this work without a calculator. So area is the depth integral from a to b of top minus bottom. So what are our a and b values? It's going to be wherever this x-intercept is, right? So this x-intercept is where in this case, 6x root 4 minus x squared is equal to 0. And the reason that we can say 6 in this moment, because we know for this particular problem, they're telling us the c value is 6. So if I were to set that equal to 0, I'll get 6x is equal to 0, and then root 4 minus x squared is equal to 0. X equals 0 here. And here, if I did square both sides, I'll get x squared equals 4. So x equals plus or minus 2. And we want to use 2 because the x equals -2 doesn't make sense, right? That's all the way over here. So we know our bounds are from 0 to 2 because of the x-intercept that we found by setting our curve equal to 0. Okay, top curve minus bottom curve. The top curve is the 6x root 4 minus x squared. And the bottom curve is the x-axis, which is y equals 0. Okay, so they want us to find the area. They want us to work through this. We can't put this in the calculator because this is a non-calculator section. So we're going to go through our process here. We can't distribute. We can't rely on power rule. So we have to rely on U substitution to get through our process. Okay. Anytime you're looking at U substitution and you're trying to figure out what the U value is, start with what's inside the parentheses. 9 times out of 10, that's going to be where your U value is. Okay. And if it's not there, at least we should look there first. So we go through our U substitution steps. Okay, so we just go through our procedure for U substitution. We let our U value be the 4 minus x squared, derivative is -2x. We make our substitutions. We need the x's to cancel out, and they will. Once we make our substitutions, the x's cancel out. The 6 and -2 gets pushed out as a coefficient of -3. We go through power rule. U to the 1/2 becomes U to 3/2 over 3/2. We clean up our coefficients. We bring back our x, and then we plug in our upper and lower bound. And you can leave your answer unsimplified. This is perfectly acceptable. Don't if it's non-calculator and if it's free response. The only time you have to maybe go a little further is, let's say, if it's multiple choice question and you're trying to figure out, okay, this is my answer. What is going to be this the matching simplified version? So multiple choice, you may want to work it a little further down to match the answer choice. But if it's free response, this is perfectly acceptable. I will leave my answer in this form once you plug in. And don't spend the time trying to get to 16. Again, if you try to clean up, just understand that if you make a mistake here, but this is correct, you'll lose points here, even though this is correct. So just try to eliminate the room for error by leaving your answer unsimplified. Okay, part C. Any questions with B? Okay, so part C. It is known that y equals cx root 4 minus x squared. Okay, so that's the shape of the curve. dy dx is this. So they're saving us a little bit of time. They're getting the derivative for us. Normally we have to go through product and chain rule and clean it up, but they're giving that to us dy dx is equal to this. So this is the slope formula for this curve, right? For a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. So we know the radius is the distance from the center to any point on the curve, right? That's the radius, right? But they say that the largest radius is 1.2. So you can imagine that this point, this radius is the largest because that's the furthest distance. But then that's also when the slope of this curve is what? Slope of this curve is also 0. So, making that connection is kind of a difficult thing, right? Well, first understanding what they're asking, what they're telling you, the largest cross-sectional circular slice, the radius of largest cross-sectional circular slice is 1.2 inches. So that means this is 1.2, but any other radius is going to be less than 1.2. So if we know that the largest radius is 1.2, that is telling us a couple of things. One thing is that that is a place where the slope of the curve is 0. And also, that's also telling us that the y value at this point is also 1.2. So it's a lot of things that we need to connect together that may not be as easy to do, when you're only, imagine working through a problem, you only have 15 minutes and you're trying to make all these connections. But that's what they're trying to get us to see. All right, so we know that this order pair has a y value of 1.2. We know the slope at this point on the curve is also 0. So we're going to take that knowledge and continue moving forward. So dy dx is 0, and y is 1.2. The radius is 1.2, but that means on the curve, the y value is 1.2. So now they're asking, what is the value of c? So we're going to put things together and try to solve for c. First, I know that my slope is 0 means I'm just going to set the numerator of my derivative equal to 0. I mean, I can cross multiply, but essentially my denominator, it doesn't play a role. I'm just going to set my numerator equal to 0, and I get x. I'm not able to solve for c, but I'm able to solve for x. I get x is equal to positive root 2. And I know it's positive root 2 because the graph is not in the negative regions. It's clearly in the first quadrant, so x equals root 2. So I know x equals root 2. I know my y value is 1.2 because I know that is the distance is 1.2 above the x-axis. And so if I know my x value and my y value, I can put all that in and algebraically solve for c. Right? Not an easy problem here. Part C is where we're actually taking this shader region, rotating it about the x-axis. So we know it's going to end up being this method because there's no gap. And we're just going through our process of going through this method. The only wrinkle in this problem is we got to keep track of that C. It's back to being a C constant. So we'll just treat C like a number and go through go through our power rule process and treat that C as a number. So my radius is just top minus bottom, the cx root 4 minus x squared minus 0. The nice thing is that once I square it, the square root goes away, but both the c and the x get squared. We can FOIL it out, go through power rule, plug in our upper and lower bound, set our volume equal to 2 pi because we know the volume is 2 pi, and then algebraically work towards solving for c. Okay, so your suggested homework tonight, pages 7 through 13, which are the 6 FRQ problems associated with the 2021 FRQs. Tomorrow we'll pick problems from the 2018, 2019 FRQs. All right, come get your phones. Okay, for those of you who don't have FRQ 5 or packet 5, I can try to print those out. If you can hang out a little bit, I can bring those back to you.
I guess.
You're in some numbers.
I don't have any children, but my sister.
Get it right.
I said it right. Oh. So just. Square. Oh, that's cheap. That is hard. Because CX equals 0. Yeah, that's one. That's another one. So two different problems. Or like two different numbers. Beats. It's all talk.
I'll go by. Yeah, sure.
A little fat man. Appreciate it. With the other 5-0. The other 5-0. That's why I'm like, you know, I don't want to spoil it. He was behind me, bro, and I was like, it's behind me. At first, he kind of set up a little. I was like, I think you're going fast. I was like 15. I was like 55. Then you split out. And you step in on the thing. Yeah, no, and then I was like, oh shit. I wanted to like speed up with me, but you didn't. I mean, I didn't want to go, you know, for breath there, right? You're not gonna hear my shit. I can hear your shit. You're not hearing mine. You hear my shit? Yeah. My shit, my music, that's yeah. I went to the room. But your car is not fast. If I get it down, faster. No, I think I was saying though, I mean, I mean, what the?
I was like, I was just doing something.
I trust her. I was right there. Said how he was talking about you. He was talking about you.
So, yeah, it's like never had that.
About like. That's what I said. I'm hungry. What should I get? Good job. All my actual name. Yeah, all my actual name. I got it. Help you up there, bro.
Okay, then maybe so.
That's what Will does, right? Every time I sit in class, the brain always does this.
I don't know, I haven't been.
Does it like? Does it backwards too? I mean, once I go, I would speed up for myself. So. Oh shit. Oh shit. You got.
Question like this. Yeah. I didn't find one word. Yeah. So we figured it out. For sure. I don't know. I'm less everything. You know what you don't. When I go down the no, what you, I'm doing that in my car, so you're fine, you say my car. I need to wait to get my, I need to wait for him to get my car there. Oh, okay. I mean, I already have so much going on Thursday, so that's one more thing. Yeah. Oh, but yeah. No, it's off. That's off. We'll give it. 2 minutes and it's but 7 pages.
No, I don't.
I was just like, I was helped time the package to 11 and one to shoot myself. Like, I'm gonna have to be doing that every night, like 50 pages to get this shit done. And I will be. So I will be too, honestly. Honestly, it's just looking better and better and just look at some things. It's not show again. Can we go? Can we go? I need to go. Can we actually go after graduation? Yeah, fuck it. So.
Can we like check into this hotel at 18?
No, but I'm gonna use my big.
Okay, so wait, can you an Airbnb at that point? Oh, but don't you get like
First
perks?
day is 25. Yeah, I need to get first. Yeah, that's up. Wait, can we actually go?
Yeah.
What day can we go?
I'm done with recital June 1st.
Okay, we still will.
Would you hate me if I worked at Pure Bar? But it's not your Pure Bar.
No.
Because my teacher Taylor works at Pure Bar, and if I like get into G or GCSU, there's a Pure Bar like 5 minutes away from the beach. So then I just have a job lined up for me already. So.
I don't know which question that.
Are you sure we don't want to spend our money somewhere else?
Like where, honey bunny? You
No, we
can't,
can
I want to go to Europe, but you can't go to Europe. Oh, I would rather go to. Yeah, I think yes, I
No,
would.
you wouldn't.
Yes, I
No,
would.
let's go.
No, I would rather go to
I
Epcot.
want to go to Yellowstone.
I want to go to Disney so bad.
What are we doing on our Christmas break? Because then I have free will at that point, so it's free range. That's absolutely my parents.
What is the problem with that?
They're thinking about this extra. They're only. Okay, can I be honest with you? The whole reason I can't see it is not too late. Basically, when she was 11, the neighbor experiences stuff happened to her, and they found her before 7. And then in high school, when she was 17, her friend went to a gas station and she got kidnapped and stuff happened to her. And then she got chopped up with one dead serious and was found behind like a store in a plastic bag. So that's why my mom is such a freak about it. It's like rooted in her. She's convinced I'm dying, and she's convinced. And my mom's mom didn't let her go out. And all because of all of that. So like that's the only way my mom thinks I'm gonna be safe. Like that's the only way. No, I know. I just have to wait. Like I really just have to wait until she can't have any recording. And it's hard telling her no because like she fully believes that it is gonna happen. Like she fully believes it because she's seen it happen. And like they really don't have to go through that at such a young age. So like it's really hard for me to tell her no. Stuff. So.
Okay, I'm.
Oh, you want me to wait here? You sure? Well, we can just come back. Like I have a second period.
I know, and then I still like to enjoy.